Hi, my name is Mia. My partners are Charlene and Matthew. Today we are going to discuss turbo machines. Turbo machines are mechanical devices consisting of several blades attached to a rotor that either extracts energy from a fluid or adds energy to a fluid as a result of dynamic interactions between the device and the fluid. They can be classified as axial flow, mixed flow, or radial flow machines. A major assumption in this chapter is that the flow moves smoothly along the blade, so that relative to the moving blade, the velocity is parallel to the leading and trailing edges of the blade. Another assumption is that the fluid enters and leaves the fan at the same distance from the axis of rotation. In this figure, the fan blade pushes the fluid from section 1 to section 2. The blade exerts a tangential force on the fluid in the direction of the motion of the blade, and therefore the blade does work on the fluid. This is a pump. In this image, a windmill shows the blades moving in the direction of the force exerted on each blade by the wind blowing through the rotor, as opposed to the rotor being driven by a motor. The blades pushed up on the fluid, opposite to the direction of the blade motion, and the fluid does work on the blades. This is a turbine. When taking into consideration angular momentum, the following equations can arise. We have the Euler turbo machine equation, an equation for shaft power, and an equation for work per unit mass. The most effective pump will have kinetic energy increasing, flow radially outward, and flow decelerated within blade passages. The most effective turbine will have kinetic energy decreasing, flow radially inward, and flow accelerating within blade passages.
Hello, my name is Matthew Petreski, and it's time to get more in depth with pumps. So when considering pumps, the most common radial flow pump is a centrifugal pump, which has two main components, being an impeller and a stationary casing enclosing the impeller. And contrary to a turbine, work is done on the fluid by the rotating blades, creating a large increase in kinetic energy and an increase in the pressure of the fluid falling through the impeller. And there's a few different types of impellers. There are open impellers, which are blades that are arranged on a hub and are open on the other side. There are enclosed impellers, where the blades are covered on both hub and shroud ends. Then there are single and double suction impellers. So for a single suction, the fluid enters only through the eye on one side of the impeller, while the double suction allows the fluid to enter through both ends. And then we also have a single or multi-stage pump. So in a single stage pump, we'll only have one impeller that is mounted on the shaft, but a multi-stage pump has several impellers that are mounted on the same shaft. A very important feature of pumps is determining their performance and efficiency. The calculation for the pump efficiency is calculated through the power gained by the fluid over the shaft power driving the pump. And this overall pump efficiency is diminished by either hydraulic losses in the pump or even further reduced by mechanical losses in the bearings, seals, destruction on the pump itself. And the overall efficiency arises from three sources: the hydraulic efficiency, the mechanic efficiency, and the volumetric efficiency. Now, on the suction side of the pump, low pressures are commonly encountered, which has a possibility of causing cavitation within the pump. And cavitation occurs when the liquid pressure at a given location is reduced to the vapor pressure of a liquid, which causes vapor bubbles to form, as well as a loss in efficiency as there's structural damage taken to the pump, which is one of the things that decreases the overall pump efficiency, as this is a mechanical loss in efficiency. And to characterize potential cavitation, the difference between the total head on the suction side near the pump impeller inlet and the liquid vapor pressure head is used. And this is the equation called net positive suction head, or NPSH. And there are only two NPSH values of interest. The first is the required NPSH to maintain or exceed so that cavitation will not occur. or the second, which represents the suction head that actually occurs for the particular flow system. So for a proper pump operation, it's necessary that the NPSH actual is greater than or equal to the NPSH required in order to make sure we have an efficient pump that does not have cavitation occur to it. Thank you.
The next topic we'll be going into are turbines, which can be classified into two types, impulse turbines and reaction turbines. In impulse turbines, the force on the blades is produced solely by turning the fluid with all of the pressure drop occurring in a fixed nozzle. An example would be the Pelton wheel. It's essentially an improved water wheel, and it's characterized by tangential flow, and is most efficient when operated at lower flow rates and with a larger head. You should note that impulse turbines convert mechanical energy to kinetic energy, and there is no net change in pressure across the rotor. In reaction turbines, the working fluid completely fills the passageways through which it flows, and the angular momentum, pressure, and velocity of the fluid decrease as it flows through the turbine rotor. Opposite to impulse turbines, reaction turbines are best suited for lower flow rate and lower head operations. Two types of reaction turbines are the Francis and Kaplan turbines, as depicted. The most efficient turbine to use can also be determined by calculating the speed and using the efficiency equation. There are also turbo compressors, which operate with the continuous compression of gas flowing through the device. There's a significant pressure and density increase, as well as considerable temperature increase. Radial flow compressors are essentially centrifugal pumps that use a gas rather than a liquid as a working fluid. Another widely used configuration would be the axial flow compressor, which has a low pressure rise per stage and a higher flow rate and is more radially compact than a centrifugal compressor. In addition, compressible flow turbines may be impulse or reaction turbines and mixed radial or axial flow turbines. Axial flow turbines are widely used, and this slide depicts a two-stage axial flow impulse turbine distribution to the left and a three-stage axial flow reaction turbine distribution to the right. So as we described, various aspects of turbomachine flow are mentioned, as well as the connection between fluid momentum and shaft torque, which help in the understanding of pumps and turbines.